This is a continuation of my series on differential forms leading up to the generalized Stokes theorem. So in the last video, we looked at mcells and m-chains and gave some examples. And today we want to look at boundaries of mcells and boundaries of m-chains. So let's recall what we saw last time. So an mcell, which we'll denote by lowercase sigma, is the image of a differentiable map from m copies of the unit interval to Rn. So it's an m-dimensional substructure inside of n-dimensional space. And it's important to point out that while we write the unit interval in the definition, often in practice we use other intervals. And that's because for all non-equal real numbers a and b, the interval a to b is diffeomorphic to the interval 0, 1, so we might as well just use that. Okay, so then an m-chain, which is uppercase sigma usually, is a formal linear combination of m-cells. So again, I'll let you look at that past video if you want to kind of recall these things. So our new definition for today, which we'll look at some examples of, is the boundary of an m-cell. So if you've got an m-cell lowercase sigma, then the boundary, which we'll denote by this like partial sigma or del sigma, it's going to be the image of this object. So we've got the sum as I goes from 1 to m, and then minus 1 to the I plus 1, so that makes it alternating. And then we have phi, where it's been evaluated in the ith spot at 1, but then it's not been evaluated at any of the other spots. So in other words, we've changed this thing from an m variable object to an m minus 1 variable object. And then minus, we've got it evaluated at 0 in the ith spot, but then not evaluated in any of the other spots. So in some sense, we're taking the function which is defining this m-cell and evaluating it at the upper and lower bound of each of these copies of the unit interval. Okay, great. So let's maybe look at a couple of examples. And so this first example is going to be a boundary of a one cell. And so we'll do like an abstract picture of this, and then we'll do an actual example or two as well. So the idea for a one cell is that that gives you a curve in Rn. So here we could have a picture. Maybe the curve starts at the point P, and then it ends at the point Q, and it's got that kind of looping action. Now I didn't discuss over here, but there's some sort of orientation to this curve. So let's say that this curve is being oriented so it's starting at P and ending at Q. So what that means is that we've got a function phi from 0, 1 into Rn, where this is our curve living in n-dimensional space. And we have phi of 0 equals P, and then phi evaluated at 1 equals Q. And so this actual object, which is the curve, in other words, the image of this function phi, that is our one cell sigma. So now if we use this definition over here, d sigma, well, we just need to sum from I equals 1 to 1, so there's really nothing to do there. That's going to give us Q minus P. So notice that's the difference of 2 points, but points are in fact 0 cells, and so this makes this a 0 chain, and so that's important to notice. So a 0 chain. So in general, you can think that the boundary of an m cell will be an m minus 1 chain. Okay, so let's do another example. So let's say our example now will be a circle. So let's say we have phi, and it's going from the interval 0 to 2 pi up to R2. So this is going to be a circle in R2, and we'll just use the standard parameterization of a circle. So let's take phi evaluated at t to be equal to the vector valued function cosine t sine t, like that. So now, just from standard multivariable calculus class, we have that the one cell, which we'll denote by sigma, is the image of this function phi. In other words, it's this circle right here. But because we know something about cosine and sine, we know this point right here will be phi evaluated at 0, and it will also be phi evaluated at 2 pi. But now we've got an orientation built into this, just like we did up here, and our orientation is rotation counterclockwise. And that's clear from our parametrization of this circle. So that means if we take del sigma in this case, we'll get the point 1, 0 minus the point 1, 0. But notice those kind of cancel each other out. Remember, a zero chain is a formal linear combination of 0 cells. So we don't want to think about this as the difference of two vectors. What we want to think about this is a formal linear combination of these two vectors. But you know, that cancels everything out. So we get essentially 0, or maybe we could think of this as like the empty set as the boundary. But that makes sense because if you've got a circle, well, there's no like 0-dimensional boundary of some closed loop. Okay, great. So let's maybe get rid of this and we'll look at a couple more examples. So for my second example, I want to look at a 2-cell. And just for the ease of use, I'm going to put it inside of R2. So let's say we've got phi, and it goes from 0, 1 cross 0 pi over 2 into R2. And it's parametrizing a portion of a disk. In fact, it's parametrizing the first quarter of the unit disk in the first quadrant. So we can do that like this. So we'll say our variables are r and theta, and here we'll have r cos theta, and here we'll have r sine theta. So in other words, we're being inspired by polar coordinates here. So that's going to give us the following picture. So we'll have this quarter of a disk in the first quadrant. And why is it a quarter of a disk? Because we're just going from theta 0 to pi over 2. So that just takes us from this positive x-axis to this positive y-axis. And I'll point out here that my radius here is just 1. Okay, great. So now let's move on to calculating the boundary here. So we'll think about this as the sum from I equals 1 to 2, and then where we've evaluated at 1 and 0 in both of the variables. But keeping in mind that our second variable is really not the unit interval, but it's the interval from 0 to pi over 2. So we need to do evaluation of our first variable first, and that'll be attached to a plus sign because we'll have minus 1 to the 1 plus 1. So that'll give us phi evaluated at 1 comma theta minus phi evaluated at 0 comma theta. Again, that's because theta is our second variable and our first variable goes from 0 to 1. Now from that, we need to subtract. And it's subtraction because we have this alternating sum right here. Phi evaluated at r comma pi over 2. And it's r because we're leaving our first variable as arbitrary. And then our upper endpoint for our second variable is pi over 2. And from this, we need to subtract phi evaluated at r comma 0, like that. Okay, so let's maybe get rid of the parentheses just so that we can see how everything is oriented. So here we'll have phi of 1 comma theta minus phi of 0 comma theta minus phi of r comma pi halves, and then plus phi of r comma 0. But now d sigma is really the image of this object here. So in other words, this is going to be a one chain. So we want to interpret each of these as 1 cells. So this is the 1 cell built out of our 2 cell up here, where we've just evaluated at r as 1. This guy right here, phi of 0 comma theta, that's going to be the 1 cell built out of our 2 cell, where we've evaluated r at 0, and then so on and so forth. So let's see the picture for each of these. So this one right here, which has been evaluated at r equals 1, but then theta is trending between 0 and pi over 2. That's going to give us this picture right here. So that's going to give us this portion of the circle. So notice we can kind of see why it is called the boundary at this point, because this is bounding the 2 cell. The 2 cell is really this solid portion in here. Okay, so now let's maybe look at this guy right here. So if r is equal to 0, then we always just sit at the origin. So that's really just giving us this point right here. And maybe how would we need to orient that? Well, to be honest, this isn't really contributing anything, so we won't worry about it so much. So now let's look at this guy right here. So we've got theta equals pi over 2. So that'll be like the positive y-axis. And then r is trending from 0 to 1. But then it's attached to a minus sign, which changes the orientation, which means that it is represented by this line segment from 0, 1 to 0, 0. And so it's going down like this. Okay, great. So now we've got one more part, and that would be this guy right here. So there we have fixed theta at 0, and then r is trending between 0 and 1. And so that's going to give us this line segment right here from the origin to 1, 0. And it's oriented in this direction. So the orientation of our 2 cell sigma has endowed the orientation of the boundary so that we're going in this counterclockwise direction around the original 2 cell. So sometimes this is written with like a little circle with an arrow on it like this. Okay, so let's maybe clean up the board and then we'll do an example of a 3 cell. So for our next example, we're gonna look at a 3 cell, and we're also gonna put it in R3 instead of a higher dimensional space just because it's simpler. And here we're being inspired by spherical coordinates. So we've got our function phi, which goes from 0, 1 cross 0, 2 pi cross 0 pi over 2 up to R3. And like I said, it's inspired by spherical coordinates. So we've got phi of r u v is r cosine u sine v, r sine u sine v, r cosine v. So r is like our distance from the origin. U is like our polar angle, so that's going to be the angle from the positive x-axis. And V is like our angle from the positive z-axis. So notice we're taking r from 0 to 1. So that's going to give us like a ball of radius 1. We have our u going from 0 to 2 pi, so that's giving us all of our polar angles. And then we have our v going from 0 to pi over 2, so that's the positive z-axis to the xy plane. So all in all, this is going to give us the top half of the unit ball. So let's maybe draw it like this. So we've got some picture that looks like this, but it's just the top half there. But then it's filled in, so it's not the top half of the sphere, it's the top half of the unit ball. Okay, so now let's calculate the boundary. So the boundary will be the image, which is described by this formal linear combination of 2 cells. So we're gonna have phi evaluated at 1 uv minus phi evaluated at 0 uv. So that's like my I equals 1 component. And from that, I need to subtract phi evaluated at r 2 pi v minus phi evaluated at r 0 v. Good. That's like my I equals 2 component. And then I need to add phi evaluated at r u pi halves and phi minus phi evaluated at r u 0. That's like my I equals 3 component down here. So now let's look at what each of these correspond to. So notice here we're setting r equal to 1. So that's like being on the edge of the sphere, but we're letting u and v range from 0 to 2 pi and 0 to pi over 2. So it's kind of hard to draw it in this picture right here, but what we're getting from the image right here, which is a 2 cell, is the top half of a sphere of radius 1. So let's maybe write that in here. So top half of the sphere. So that does not include the disk on the bottom. So that's important to notice. That's just the top half of the sphere. Okay, great. So now let's talk about this guy right here. So here we've got the R is always 0. So the distance away from the origin is always 0, but then U and V can be any angle. So again, that's really just going to give us the origin, the single point. But again, since we're working with 3 cells and their boundaries, which make 2 chains, then that doesn't really contribute anything meaningful. So we can go ahead and disregard this object right here. And I should say we're disregarding this in like a geometric sense. Okay, so now let's look at these 2 portions right here. So here our R is variable and our V is variable. So remember, R is the distance away from the origin and V is that angle from the positive Z axis. But in this component we fixed U at 2 pi, and in the other component we fixed U at 0. But just from a purely analytic sense, we know having U equal to 2 pi and U equal to 0 will give us the same sort of object, so those are going to cancel. But if you want to think about that geometrically, this object is going to be like the sliver starting up here and going down to the positive x-axis. So it's going to be like half of a disk. But that disk lives between the positive z-axis and the positive x-axis. And this is going to be exactly the same thing, but oriented in the other direction. But any way you slice it, these 2 guys cancel each other. So let's see what we've got left. We've got this bit right here where R is variable, U is variable, but V is fixed at 0. But fixing V at 0 means we're just pointing in the positive z-axis direction the whole time. But if we're just pointing in the positive z-axis direction the whole time, then that's really just going to leave us at a single point, which is like the north pole of this unit ball or this sphere. But again, because that north pole is like a 0-dimensional space, we don't really need to worry about it as much from a geometric point of view, so we can cancel this as well. And then what about this, which is the one thing that's left over? So notice that R is variable, U is variable, our polar angle, but V is fixed at pi over 2, but pi over 2 is the xy plane, but that's going to correspond to parametrizing a unit disk in the xy plane. And we can see that very, very clearly if we just evaluate all of these V's at pi over 2 and see we get the vector valued function R cosine U, R sine U, and then finally 0 because cosine pi over 2 is equal to 0. So notice that just gives us the standard parameterization for a unit disk. So this is maybe the disk at the bottom. So what I mean by that is it's like this bottom part of our unit ball. So notice that the 2 objects that contributed meaningful parts to this boundary contributed this top half of the sphere and then this bottom part. So this notion of boundary geometrically is backed up by this careful definition of the boundary of this M cell. Okay, so now that we've looked at some examples, we need to look at the boundary of an M chain, not just an M cell. And so I'll clean up the board and we'll end with that definition. So now that we've looked at some examples, we can look at the definition of the boundary of an M chain. And this is like super quick. And that's because the definition of an M chain is really just a formal linear combination of M cells. So this definition of the boundary of an M cell goes on to the boundary of an M chain just linearly. So if capital sigma is an M chain, so in other words, like I said, it's a formal linear combination of M cells. So here we have our capital sigma is the sum over I of Ni times sigma I, where the Ni are just numbers and the sigma I are our M cells. And I know it's like kind of sloppy to have this summation symbol be a sigma, and then we're defining this M chain as a sigma as well, but I think that's fairly standard, unfortunately. So del sigma, or the boundary of this M chain, is just going to be defined as the formal linear combination with the same numbers of the boundary of all of the corresponding M cells. So that's really all there is to it. So since we've done some examples calculating boundaries of M cells, well, that just goes linearly into boundaries of M chains. And that's a good place to stop.